Alright, this is the example on slide 4 of our chapter 20 part 2 PowerPoint. And in this example, we are going to be calculating the delta G naught, or standard free energy of our reaction, using the negative NF Ecell potential to plug into the equation written here. So, question states to use the tabulated electrode potentials to calculate delta G for the reaction, and then, once that's calculated, to determine if the reaction is spontaneous or not. So the first thing we're going to be doing for this problem, before we can plug all our numbers into the delta G equation, we have to figure out what our standard cell potential is. That little symbol E naught cell. So in order to do that, we're going to have to first identify what reactant is oxidized or reduced, then split this one reaction into its two half reactions, and to look at our standard cell potential table to figure out the standard cell potentials for each half reaction, which we can then first plug into the equation E cell is equal to the standard cell potential of our cathode minus the standard potential of our anode. So if you have your table, I would have that ready for consultation. And I will go ahead and post the standard cell potentials as a separate document in our module for this week. I meant to do it last week, but apparently forgot. But it is in your slides on the chapter 20 part 1 for looking at. Alright, so first things first, in this reaction we need to identify what's reduced and what's oxidized, so we can therefore translate those into half reactions. So to do that, we got to figure out the oxidation numbers of every element. So iodine, standard state by itself, oxidation state of 0. Br minus has a -1. Iodine minus is -1. And then Br2 in its standard state by itself is 0. So in this, our bromine is being oxidized, and I have a little color coding there, hopefully you can see, and our iodine is being reduced. So now that we know that, we can separate these into their separate half reactions. So our oxidation, which is occurring at the anode, is 2 Br minus gives you Br2 and 2 electrons. And our electrode potential, cell potential is added together. For that guy, if you consult your table, remember these are written as reduction, so you just need to look for Br2. Our standard electrode potential for the Br2 half reaction is 1.09 volts. And that is our anode cell potential. So basically what we did, we just wrote the oxidation half reaction with the included electrons. And to make sure everything's balanced, so that's why there's a 2 in front of the Br minus. So second is our reduction, which occurs at the cathode. So in case you haven't figured it out by now, oxidation always occurs at the anode, reduction always occurs at the cathode. And in order to remember that, just remember reduction, cathode. So our cathode reaction, reduction reaction, is I2 plus 2 electrons gives you 2I minus. And if we look at our table, the standard electrode potential for the cathode for iodine is 0.54 volts. So whenever we're doing these, if for some reason you have to multiply your reaction by a coefficient, you never change the standard cell potential. It always is what it is. So in this case, we didn't have to manipulate either of our equations. So basically, in order to make sure that our redox reaction is balanced, we need to add these two half reactions together. So I'm going to do that now. I'm adding my oxidation to my reduction. Make sure my electrons cancel. And it gives me 2 Br minus plus I2 produces Br2 plus 2I minus. Basically, we just have to make sure those are balanced. They add up to what the total reaction is up top. And then we can perform our calculation for our standard cell potential, which is our cathode minus our anode. So that's going to be 0.54 volts minus 1.09 volts, which gives us a standard cell potential of negative 0.55 volts. So that's first part of our reaction, or our problem that we're working. We had to get our standard cell potential to plug into our ΔG equation. Alright, so next on our list is to basically plug into our ΔG equation. So ΔG is equal to negative N. N is moles of electrons transferred. And we can get that value by looking at our half reaction and seeing we have 2 total electrons either given or taken away. So N is equal to 2 moles of electrons. And F is something called Faraday's constant, and it is equal to 96,485 coulombs, which is a unit of electrical current, per 1 mole of electrons. So hopefully you've seen this in the slides previous to this, but that's what F stands for. It's Faraday's constant. It's always the same value, 96,485 coulombs per coulombs of charge per 1 mole of electrons. Alright, so now that we have all the items we need to plug into our equation, I'm going to change to the next slide where we have all that information written. And we're going to plug in for our ΔG equation. So ΔG is equal to negative 2 moles of electrons times Faraday's constant, 96,485 coulombs per 1 mole electrons. Times our standard cell potential, which is negative 0.55. And I'm going to go ahead and change the volt unit. So standard cell potential is reported in volts. Technically, 1 volt is equal to 1 joule per coulomb. And I'm going to do that so that coulombs can cancel, and we want our end unit to be in joules, our ΔG. So I'm breaking volts into its 2 constituent units. So 0.55 joules per coulomb. That means moles are going to cancel out, moles of electrons. Coulombs are going to cancel, and we'll be left with units of joules, which is what we want our ΔG to be in. So now if we just multiply these 3 numbers by one another, our ΔG is equal to 1.1 times 10 to the 5th joules. And that is your final answer one more part we need to answer is if this reaction is spontaneous or not. So since our delta G is positive, remember positive delta G means non-spontaneous. Therefore, our reaction is non-spontaneous. So it's not spontaneous under these conditions. And that's it for that example.